Hey, welcome back. So we're going to look at how to write any Lewis structure. And so far I've kind of picked examples that you click the atoms together, right? And you just basically have to make sure that the electrons come so that there's 8 around each atom, giving you a nice stable octet. But they're not always going to be this simple. And I'm going to go ahead and write out a set of rules for how to write Lewis structures. And I'd highly recommend you sort of copy these rules down in your notes and you just refer to them. And kind of like driving a car, where after you've driven it for a while, you really just kind of know how to do it. After you've written a lot of Lewis structures, you sort of know how to do it. And the only time you would ever look at these notes again is if it's 10 years down the road and it's 2030 and you're like, oh my gosh, how do I remember how to write this stuff? Or, if you're going to go ahead and teach chemistry maybe in high school or college or something where you might recopy these rules onto the board. So let me go ahead and just write them up. So the first rule is find the total number of valence electrons. And how do you do that? The answer is you look at the group number the atom is in, and the group number is almost always the number of valence electrons. And the kicker is that we have to remember to remove electrons to make positive charges, and we have to add electrons for negative charges. So we've got a polyatomic ion, we've got to take that into account. So let's go ahead and get started. So if we take something like NH3, NH3 is ammonia, and I like to do this exactly the same way every time. So I am a complete stickler for doing things exactly the same way every time. You've got one nitrogen, so nitrogen is in group 5, so we got 5 valence electrons. We've got 3 hydrogens, so hydrogen's in group 1, but we have to remember that if there's 3 of them, we have to triple that 1 electron. So each hydrogen has 1 electron, so 3 hydrogens will have 3 electrons total, and that gives us 8 electrons to play with. And if we go to something else, like for instance the sulfate polyatomic ion, SO4 2-, sulfur is in group 6, oxygen is in group 6, and we have to remember that there are 4 oxygens, so we have to multiply that last 6 by 4. And here's the kicker, right? So this negative charge up here, in fact it's not -1, it's -2, comes from the addition of 2 electrons. So you gain 2 electrons to gain a 2 negative charge. Electrons are negative, remember. So what does that give us? So 6 plus 4 times 6 plus 2. Let's see, 4 times 6 is 24, plus the 6 up front is 30, plus the 2 on the end is 32 valence electrons. So not core electrons, just the valence ones. If we had something crazy like pH4+, I don't know if that one actually exists or not, then phosphorus is in group 5 and hydrogen is in group 1. We've got 4 hydrogens, so we multiply that by 4. And then the positive charge, well, we create a positive charge by losing an electron, so we subtract 1, and I think we get 8 valence electrons from that. So that is rule number 1. So I kind of like to do this bit by bit, and then we'll put it all together in a moment. So rule number 2 is to write out the skeleton structure, and the skeleton structure, kind of like your bones represent the skeleton in your body, that kind of gives you the connection of the atoms with one another. And how do you write the skeleton structure? Well, if I got something like NH3, what I'm going to do is I'm going to put the N in the middle, and I'm going to put the H's around it, and I'm going to write a line in between the N and each one of those H's. And the question is, how do you know the skeleton? How do you know how it looks like? And very roughly, we're going to have sort of a hub and spoke model. So we're going to have one atom in the center, and the other atoms are going to go around it. So we've got the spokes going around the outside of the hub, I suppose. And we're almost always going to put hydrogen and halogens, those are the elements in group 7, on the outside. And so those would go at the end of the spokes, if you like. So that is in these positions here. So since we have hydrogens, we almost always put them on the outside. If you've got a single atom, it is almost always going on the inside. And that's probably enough for us to get by for now. And the other rule is we tend to try and keep it as symmetrical as possible. So that's kind of a bluff your way to a skeleton structure. So if we had something like SO4 2-, okay, now we don't have any hydrogens or halogens here, so halogens group 7, hydrogen, well, just an H. But the single atom often goes on the inside, so we look at the S and we say there's only a single atom of that element, so that probably goes on the inside, and those oxygens go around it. So we're going to have 4 around it, and we're just going to draw a line, kind of hub and spoke, so we're going to connect the center to the outside. Otherwise, it would be 5 individual atoms. Now it's a single structure. And the very last one we had, I think, was P PH4 plus. So again, we've got hydrogens. They're probably going to go on the outside, and the phosphorus goes on the inside. And again, there's just one phosphorus, so it'll almost always go on the inside. So it's going to look something like so, and that's our spooky skeleton structure. Once we've written our skeleton structure, we want to keep track of electrons. So we have to always account for them. So I'm going to go ahead and draw this in blue. So ammonia, so NH3, started out with, I believe, 8 electrons. And we have to do the count. So we used a bond here, a bond here, a bond here. Do you remember how many electrons are in a bond? A single bond. That's right, it has 2 electrons. It has a pair of electrons. So there's 2, there's 2, there's 2. So I've now used up 6 electrons at this point. So I just kind of keep a tally, and there I've got 2 electrons left. SO4 2 minus, I believe, started with 32 electrons, and we have to subtract out these bonds. So there's 2 in each bond, so there's 2, another 2, another 2, another 2. That's a total of 8. So what we have to do here is just subtract 8 away from 32, and that gives us 24. And if we go to PH4 plus, I'm not actually sure PH4 plus is a real thing, but we started with 8, and each bond was 2. So if we've got 4 bonds, how many did we use up? Yep, that's right. We used up 8 electrons, and so at that point there, we are completely out of electrons. So our bottom line here is we've got 2 remaining electrons here, 24 here, and we are completely out of fun on this one. So, okay, what's next? So our third rule is we're going to add electrons in pairs, so they always go in pairs, to outer atoms until they've got an octet, or in the case of essentially just hydrogen, a duet. So we can go to our first one we had on the last screen, so that was NH3, and let's see, we had N surrounded by 3 H's, something like that, and I believe we had 2 leftover electrons, and well, actually, we can't add it to the outer atoms here, and why not? And the reason we can't add them is that those outer atoms are hydrogen, and when we look directly around that hydrogen, how many electrons does it have around it? And the answer is it has 2 right there. That bonding pair is actually 2. So if I go ahead and just kind of circle this, just to kind of show you what I'm on about here. So there's 2 kind of right there. So it doesn't actually need any more. So it satisfies the duet rule at that point there. So we're actually done with NH3. That wasn't too bad. If we go to the next one was sulfate. So that's SO4 2 minus. And I believe we had a total of 32 electrons. And oh, wait a minute. No, we subtracted 8 for our bonds. That gave us 24. And now we get to go ahead and add them to the outer atoms until they've got an octet or a duet. So if we look around this oxygen here, it's got 2 electrons from this bond. So how many more does it need to have an octet? Yep, that's right. It needs 6 more, so to have a total of 8. And we always add them in pairs, so we can go ahead and just kind of put them 1, 2, 3, 4, 5, 6, okay, and it already has 7, 8 from this bond here. And we just go around the molecule, and or the ion, I suppose. And actually, since each oxygen already has 1 bond, each oxygen already has 2 electrons around it, so each one needs 6 more in order to have an octet. Notice I'm keeping them paired up here. So if you ever write the electrons not paired up, so not like little colon marks, then that's unpaired. And they're highly reactive, highly dangerous, free radical species. So never want to write them like that. How many electrons do we have? We want to keep track. So let's see, 1, 2, 3, 4, 5, 6. And another one, and another one, another one. So 6, 12, 18, 24 electrons we've just used up. So if we keep tally, we are completely out of electrons on that one. And if we go to our last one, which was this PH4 monster, so PH4, and how many electrons do we have left on that one? We had 0. Okay, so there's really nothing we can do on this one here. So we need to go to the next rule. So rule number 4 says all remaining electrons have to be placed on the center atom. And I think there's only one of our structures so far that has any leftover electrons, and so that is NH3. So NH3, at this point here, we started with 8 electrons, and we used up 6 from those covalent bonds, leaving us 2 left. And then the last rule says all remaining electrons go on the center atom. So we basically take that center nitrogen, and we use up all of them in pairs. So if there was 4, we would have put 2 pairs of electrons. If there were 6 left over, we would have put 3 pairs of electrons in there. And that gives us our completed rule number 4. And I always like to think about this as pixie dust. I don't know why, it just helps with my mind's eye, I suppose. Poor Tinkerbell there, I should probably get rid of that image. And the pixie dust, we kind of sprinkle on the molecule itself. And we sprinkle it from the outside to the inside. So all the electrons we start with in rule number 3, we add to the outer atoms in pairs, so they have their octet or duet. And only when we've done the outer ones do we put them on the inner ones. So you can think of this as a pizza. You eat from the outside to the inside. We place our electrons from the outside to the inside. Now, the very last rule, actually I think there's one more after this, so the very last but one rule here is if the central atom's got less than 8 electrons, we make multiple bonds by sharing lone pairs on the outer atoms. So that's kind of a mouthful, so where would be a situation where we might worry about this? Golly gosh. So let's say we've got something like CH2O. And CH2O, so this isn't a very good one actually, but I'll go ahead and give you the skeleton. The skeleton is the carbons in the center, and the hydrogens and the oxygens around the outside. How many electrons do we have? Carbons in group 4, hydrogens in group 1, so we got to remember to double that. Oxygens in group 6, so that's a total of 12 electrons. Those 12 electrons, then we make a bond between the center atom and the outer atom, so that uses up a total of 6. So that leaves us with 6 left. And what do we do with those 6? Well, then we put them on the outer atoms and then the inner. The outer ones, the hydrogen's got 2 electrons around it. Remember, hydrogen only needs a duet, so it's actually fine. Same over here. But this oxygen here, right, needs an octet. It's got 2 electrons here. It needs another 6 to complete its octet. So let's go ahead and put another 6. 1, 2, 3, 4, 5, 6. And bingo, we are completely out of electrons. So is this a valid Lewis structure? Well, it would be if the central atom had 8 electrons around it, but it has 1, 2, 3, 4, 5, 6, so it needs 2 more. And you can't just reach into the ether and put 2 more on it because you can't borrow electrons here. So what we have to do is we have to share, and the easiest way you can think about doing that is we're just going to kind of take any one of these lone pairs here, and we're going to share it. So we're going to kind of move it in between the carbon and the oxygen. So let me just go ahead and redraw over on the side. So there's my lone pair. There's my lone pair. And that third lone pair is no longer there. It's gone, and it's in between the atoms now. So that's converted from a single bond to a double bond. And actually, if I drew this more carefully, right, the double bond we know is stronger and shorter, so I should probably shrink down the size of that bond there. But that's how we would handle the center atom being short. Almost forgot to do this one. So the very last rule is only applied if it's an ion. So I had SO42 minus the sulfate ion, and last we left it, right, we had a structure that looks something like this. And gosh, drawing those pairs of electrons is kind of a pain, but there we go. It's actually easier on my iPad. And since it's got a 2 negative charge, we have to put the charge on the structure, and we don't want to say at this point what atoms inside have the charge. So the convention is just to encase in those square brackets and write the charge, something like that. So we had another one, right? So NH4 plus. No, it wasn't, right? It was PH4 plus. Whether it's real, I'm not really sure. So we had P surrounded by 4 H's, something like that. And the very last thing we should have done is encased it in those square brackets and put the plus next to it. So that's it.